For years, one sentence echoed through the semiconductor industry almost like a law of physics. Advanced chips don't become commercially viable just because you can produce one. They become valuable when you can produce millions of them with almost no defects. That was supposed to be China's biggest obstacle. Design could improve. Equipment could evolve. But manufacturing yield? Western analysts repeatedly argued that process know-how, accumulated over decades by companies like TSMC, Samsung, and Intel, couldn't simply be recreated. Then a very different number started circulating: 96%. If that figure is even close to reality, we're no longer talking about China proving it can manufacture chips. We're talking about China approaching the efficiency levels that determine whether an entire semiconductor ecosystem can sustain itself without relying on foreign production tools. That's a very different conversation. And it forces us to ask whether one of the industry's longest-held assumptions is beginning to crack. Not overnight, not magically, but gradually enough that many people simply haven't noticed. Yield rate sounds like a technical metric that only engineers care about. In reality, it's one of the most important numbers in the global economy. Imagine baking 100 cakes. If only 60 come out properly, your ingredients, electricity, and labor costs suddenly become far more expensive for every cake you actually sell. Semiconductor fabrication works the same way, except each silicon wafer can be worth tens of thousands of dollars before it's even cut into individual chips. A few percentage points can decide whether a factory earns billions or burns billions. That's why, after export controls expanded in 2022, many analysts weren't just questioning whether China could build advanced fabrication equipment. They questioned whether those tools could ever achieve stable, profitable production. Manufacturing isn't just about precision. It's about repeating that precision every single day, across thousands of wafers, without tiny defects multiplying into enormous financial losses. The skepticism wasn't irrational. Companies such as ASML, Applied Materials, Lam Research, and KLA spent decades refining equipment, inspection systems, software, and process integration. That experience created an enormous advantage. You can purchase machinery. Buying 40 years of manufacturing experience is considerably harder. Yet China's semiconductor strategy never depended on copying one company. Instead, Beijing poured support through the National Integrated Circuit Industry Investment Fund, often called the Big Fund, while domestic suppliers developed individual pieces of the manufacturing chain. One firm focused on etching, another specialized in deposition. Others concentrated on metrology, cleaning systems, or process control. None replaced Western suppliers alone. Together, however, they slowly reduced dependence. It's a remarkably unglamorous strategy. No dramatic announcement, no cinematic breakthrough. Just thousands of engineers solving one production problem after another. Ironically, sanctions designed to slow that effort may have strengthened the incentive to finish it. That doesn't automatically mean every reported success should be accepted without question. Semiconductor manufacturing is famous for selective reporting, and yield percentages can vary depending on the chip, the production stage, and how they're measured. Healthy skepticism is still necessary, but skepticism should work both ways. Assuming success is impossible can become just as misleading as assuming every headline is true. Because the real question isn't whether one factory reported a high yield. The real question is what happens if several domestic production lines begin repeating those numbers consistently. If that happens, the discussion shifts from technological survival to industrial competition. And that changes the semiconductor landscape far more than a single percentage ever could. The surprising part is that the yield figure itself may not be the biggest development. The manufacturing philosophy behind it might be. And that's where this story becomes far more interesting. Manufacturing experts often describe semiconductor fabrication as an orchestra rather than a single instrument. The public usually focuses on one machine, typically the lithography system, but a modern chip passes through hundreds, sometimes well over 1,000 manufacturing steps before it leaves the factory. etching, deposition, ion implantation, polishing, cleaning, metrology, defect inspection, packaging. Every stage has to cooperate almost perfectly. One weak link can destroy the yield of an entire production run. That's why the phrase Western process know-how carried so much weight. It wasn't simply about owning advanced equipment. It referred to thousands of small manufacturing decisions accumulated over decades. Which chemical mixture reduces microscopic contamination? How long should a wafer remain inside a deposition chamber under different humidity conditions? Which inspection algorithm detects defects before they multiply? None of these questions sound dramatic, but together they determine whether a chip works or ends up in the scrap bin. For years, companies like TSMC and Samsung Electronics benefited from that accumulated experience. Even when competitors purchased similar categories of equipment, matching production efficiency proved far harder than matching specifications on paper. China recognized this problem earlier than many people realized. Instead of trying to leap directly into the world's most advanced nodes, domestic manufacturers increasingly focused on mastering production discipline. SMIC, China's largest contract chip manufacturer, invested heavily in improving process stability alongside capacity expansion. At the same time, equipment suppliers such as Nora Technology, Advanced Microfabrication Equipment Inc., AMEC, and several metrology specialists gradually expanded their capabilities across different manufacturing stages. That strategy rarely generated exciting headlines. Investors generally celebrate the newest chip design or the smallest transistor size. Nobody rushes to social media because an inspection tool reduced particle contamination by a fraction of a percent. Yet that's exactly how manufacturing leadership is built. One engineer once compared semiconductor production to running a hospital. Buying the world's best surgical equipment doesn't automatically produce the world's best surgeons. Procedures, training, repetition, and experience matter just as much. Semiconductor fabs operate under the same principle, except every mistake costs millions instead of one operation. This is where reported yield improvements become economically significant. Suppose a factory produces 10,000 wafers every month. Increasing usable output from 80% to 96% doesn't simply add 16 percentage points. It dramatically lowers production cost per functioning chip because expensive materials, electricity, and machine time are no longer being wasted on defective products. The financial difference compounds across millions of processors, memory chips, or AI accelerators. That's why governments care. Semiconductors aren't just another export industry anymore. They sit underneath artificial intelligence, telecommunications, electric vehicles, cloud computing, industrial automation, military electronics, and consumer devices. A nation capable of manufacturing advanced chips consistently gains resilience across multiple industries simultaneously. Of course, critics raise an important counter-argument. Some analysts argue that isolated reports of high yield don't necessarily represent nationwide capability. That's a fair point. One successful production line is very different from dozens operating at commercial scale year after year. History is full of impressive laboratory achievements that never became sustainable businesses. But there's another side to that argument that deserves equal attention. Manufacturing maturity rarely arrives with a single dramatic announcement. It usually appears as a collection of small improvements that outsiders dismiss individually until, one day, everyone realizes the industry has quietly crossed a threshold. We've seen this pattern before. Japan followed it during the 1970s and 1980s. South Korea experienced something similar in memory chips. Taiwan gradually built an ecosystem that eventually became indispensable to global semiconductor manufacturing. None of those stories were driven by one miracle invention. They were built through relentless process optimization. That historical perspective makes today's developments harder to dismiss. Whether the reported 96% yield ultimately proves completely accurate or settles somewhat lower is almost secondary. The more important signal is that discussion has shifted away from asking whether domestic equipment can function at all. Increasingly, the debate revolves around how competitive that equipment has become. And once the conversation changes from possibility to competitiveness, the strategic implications extend far beyond a single fabrication plant. The next question isn't about one company anymore. It's about whether an entire supply chain is beginning to stand on its own. There's another reason the reported yield figure deserves attention, and it's one that often gets lost behind discussions about nanometers and lithography. A semiconductor industry isn't judged only by how advanced its best chip is. It's judged by how resilient the entire ecosystem becomes when something goes wrong. That distinction matters. The export controls introduced over the past few years were designed around a simple assumption. If China couldn't access the most advanced manufacturing equipment, its technological progress would slow dramatically. On paper, the logic made sense. Restrict access to extreme ultraviolet lithography, tighten controls on high-end chip-making tools, and the gap should widen over time. Reality has been more complicated. Instead of abandoning semiconductor ambitions, China redirected enormous resources toward domestic substitution. Ministries expanded support for strategic technologies, provincial governments competed to attract semiconductor investment, universities increased engineering programs, and private firms accelerated research that had previously looked too expensive or too risky. Critics sometimes dismiss this as state spending replacing market efficiency. There's truth in that criticism. Throwing money at an industry doesn't guarantee innovation. China has experienced failed chip projects, bankrupt startups, and wasted billions over the past decade. Building a semiconductor ecosystem is one of the hardest industrial challenges on Earth, and financial support alone cannot manufacture engineering talent. But here's where the picture changes. Failure isn't unusual in semiconductor history. It's almost mandatory. The United States, Japan, South Korea, and Taiwan all spent decades making expensive mistakes before becoming manufacturing leaders. Looking only at failed Chinese projects while ignoring successful ones creates an incomplete picture. Remember that 96% yield from the beginning? Whether the exact number proves sustainable is still something the industry will continue watching. Yet, even if future data adjusts it slightly, reaching anything close to that level using increasingly domestic equipment would suggest that Chinese engineers aren't merely assembling machines, they're learning how to optimize entire production systems. And optimization is where long-term competitiveness is born. Here's the reversal that makes this story more interesting. Many observers assumed sanctions would freeze China's semiconductor capabilities in place. Instead, they may have accelerated the development of technologies that otherwise would have remained dependent on foreign suppliers for much longer. Necessity can become an expensive research program. That doesn't mean sanctions failed completely. Far from it. China still faces meaningful challenges in areas like cutting-edge EUV lithography, certain advanced inspection technologies, high-performance electronic design automation software, and some specialized semiconductor materials. Those are genuine obstacles, not minor inconveniences. The gap at the absolute frontier hasn't disappeared. However, global competition isn't determined only by whoever reaches the smallest transistor first. It's also determined by who can reliably manufacture enormous volumes of commercially useful chips across automotive electronics, industrial automation, telecommunications, consumer devices, and increasingly, artificial intelligence hardware. Sometimes people imagine semiconductor competition as a 100-meter sprint. It's closer to running an entire marathon while simultaneously building the road beneath your own feet. That changes how we should interpret manufacturing data. If domestic equipment consistently produces commercially viable yields across multiple fabrication plants, international customers, suppliers, and investors begin evaluating Chinese alternatives differently. Confidence grows slowly, but once established, it becomes remarkably difficult to reverse. I also think there's a psychological dimension that isn't discussed enough. For years, conversations centered on China's technological limitations. Increasingly, they revolve around China's technological trajectory. Those are two entirely different questions. One asks what can't be done today. The other asks where capabilities might be 5 or 10 years from now. History suggests trajectories often matter more than snapshots. Which brings us to the biggest question of all. If manufacturing yield is no longer the bottleneck many experts believed it would remain, then what becomes the next decisive battlefield? Because every technological race eventually shifts from proving something is possible to deciding who can scale it faster, cheaper, and more reliably. The answer may end up being less dramatic than either side expects. China doesn't need to dominate every category of semiconductor technology to reshape the industry. It only needs to become sufficiently self-reliant in the areas that matter most to its own economy. That's a lower bar than complete technological supremacy, and arguably a more achievable one. Think about the scale involved. China is the world's largest consumer of semiconductors. It imports hundreds of billions of dollars worth of chips because everything from smartphones and electric vehicles to factory robots and data centers depends on them. Even replacing a fraction of those imports with competitive domestic production represents an enormous economic shift. This is where yield rates become more than engineering statistics. A factory producing high-quality chips consistently attracts customers. Customers generate revenue. Revenue funds research. Research improves equipment. Better equipment raises yields even further. It's a cycle that reinforces itself. The opposite is equally true. Low yields increase costs, discourage investment, and slow innovation because companies spend more time fixing manufacturing problems than developing the next generation of technology. That's why the reported 96% figure matters far beyond a single fabrication line. If repeated across different facilities and products, it signals that China may be entering the self-reinforcing stage of industrial development rather than the catch-up stage. That doesn't mean Western semiconductor leaders are suddenly in trouble. Companies such as ASML, Applied Materials, Lam Research, KLA, TSMC, and Samsung Electronics still possess extraordinary technological advantages, particularly at the leading edge. Their research budgets, customer relationships, engineering talent, and decades of manufacturing experience cannot be replicated overnight. Those strengths remain very real. But competitive landscapes rarely stay frozen. History repeatedly shows that today's technological lead can shrink when competitors improve faster than expected. Japan challenged American semiconductor dominance. South Korea transformed the memory market. Taiwan became indispensable to advanced chip manufacturing. None of those transitions happened because the leaders suddenly became weak. They happened because challengers gradually became stronger. China appears to be attempting the same journey, although under very different geopolitical circumstances. My own view is somewhere between the extremes. I don't think every optimistic headline about China's semiconductor industry should be accepted at face value. Independent verification remains important, especially when reported manufacturing metrics can influence markets and politics. Healthy skepticism protects us from believing numbers simply because they sound impressive. At the same time, dismissing every achievement because it doesn't fit older assumptions is equally risky. Technology evolves, engineers learn, supply chains adapt. The semiconductor industry has always rewarded persistence more than publicity. Remember the assumption we started with? The belief that advanced manufacturing required Western process know-how accumulated over decades? Perhaps that statement was never entirely wrong. The more interesting possibility is that process know-how isn't something permanently owned by one group of companies. It's something that can gradually be developed, refined, and transferred through years of experimentation, failure, and relentless improvement. That process is painfully slow, but it isn't impossible. If reported yields around 96% become normal rather than exceptional, future historians may look back and say the real turning point wasn't the day China produced another advanced chip. It was the day people realized Chinese factories had learned to produce those chips efficiently, consistently, and at commercial scale. That's a much bigger milestone. The semiconductor race isn't ending. If anything, it's becoming more competitive than at any point in decades. And when competition intensifies, innovation usually follows. We'll be watching the data, not the slogans. Because in this industry, wafers don't care about politics. They only care whether the process works. And increasingly, that may be the number that tells the real story. If you enjoyed this breakdown, subscribe for the next one. The biggest shifts in technology often begin with numbers that most people overlook until they become impossible to ignore.